Hello everyone, so welcome to lecture 3 of week 3. So we'll continue our discussion on how do we learn word representations. So we'll continue our discussion on the skip-gram model and see the negative sampling and hierarchical softmax formulations, and also we'll talk about the glove word vectors that are another very important word vectors along with word2vec. So what were the issues that we identified with word2vec? So one was the computational overhead. So we saw that we have to compute this quantity. So UO transpose VC divide by summation over all words in vocabulary UW transpose VC. Now what was happening? So this I am computing for each word in the vocabulary, and this becomes very computationally expensive computing this. So there are some formulations that avoid this. So they are called negative sampling and hierarchical softmax, and at the end they end up optimizing a slightly different objective function. So we will try to see in detail what kind of objective function do they use. So consider the negative sampling, right? So what is the formulation? This is inspired from noise counterstive estimation. So let's say we have a pair of a word and the context. So W is the word and C is the context. Now the question that we ask in negative sampling is formulation is, did this pair come from the training data? So let's say probability d is equal to 1 given WC denote that the probability that WC came from the corpus data. So it's like a positive sample, and d is equal to 0 given WC is the probability that it did not come from the corpus data. It's a negative sample. And what we do, we model this probability of d is equal to 1 given WC using a sigmoid function. So d is equal to 1 given WC and the parameters that I am learning, it's sigmoid over, so C has a vector VC and W has a vector VW. So VC transpose VW, and this formulation is very similar to the taking the dot product of vectors, is very similar to what we saw earlier, but now I am modeling this entire phenomena using a sigmoid. So this is 1 upon 1 plus exponent minus VC transpose VW, and you can see what is happening in sigmoid. If this quantity is high, so if the similarity is high, this is a minus, it's a high minus, say something like minus 10, and e to the minus 10 will become close to 0, and this 1 upon 1 plus 0 will become close to 1, right? And if the similarity is very low, so then this will be 1 upon 1 plus e to the 0. So this will become a small value, right? So I would like, if they are coming from corpus data, I would like this embedding similarity to be high, right? So now this is what I want to maximize, the probability of a word in a context being in the corpus data if it indeed is, and the probability of a word in context not being in the data if it is not. So for all WC pair that I have seen in the data, I want to maximize this probability, and for all pair that I have not seen in the data, I want to maximize this probability, that d is equal to 0. Fine, and probability d is equal to 0 is nothing but 1 minus probability d is equal to 1 given this. Now we have already formulated it using this particular sigmoid function. This is 1 upon 1 plus exponent minus UW transpose VC, and this is 1 minus 1 upon 1 plus exponent UW transpose VC, right? And 1 minus this will become 1 upon 1 plus exponent UW transpose VC. So this will be 1 plus exponent minus UW transpose VC minus 1 divided by 1 plus exponent minus UW transpose VC. This cancels out, and then I again divide by this quantity. So I will get 1 upon 1 plus exponent UW transpose VC, right? That is what I get here. Okay. So this is what I want to maximize. Now, so because we want to minimize something, minimize the loss, so corresponding loss will be minus of this. So I take the negative log likelihood, this was a log likelihood, and I take the negative log likelihood, that becomes my loss function. So for all pairs that I have seen in the data and all pairs I have not seen in the data. So this is the loss, negative log likelihood loss. Now d hat is just a false or negative corpus. So what we can do, we can generate this negative corpus on the fly by randomly sampling from the word bank. So let's say we sample, so this we already know which word came in the context of another word. So this I can already write minus log sigmoid of UC transpose V hat. But this one, what I will do, so V hat is constant, this is the word in context, and this is a word that is a negative sample. So I will do minus sigmoid of minus UK tilde transpose V hat, where I have taken k is equal to 1 to k negative samples. Right. Now, how do I actually pick up negative samples? So in the paper, what they did, so they use P and W, where PW is nothing but a unigram probability distribution. So you know from your data what is the unigram probability for individual word, but you raise it to 3 to the power 4. Right. So it's the probability of a word to the power 3 by 4 and normalize that. So what happens as a result, because if you don't normalize, every probability will go, will become larger, right? So you raise it to the power 3 by 4, and so the impact it has is mainly for words that have very low probability. So by raising it to the power 3 by 4, you end up increasing their probability, right? So this becomes 0.032, while 0.9 to the power 3 by 4 becomes 0.92. It has small impact, but you get larger impact here, and of course you will do a normalization over that. So this at the end will become smaller than 0.9, but this value will become much larger than 0.01. So the words that are rare will also get high chance, have a high chance on appearing in the sampling process. So this is the negative sampling idea. So let us take an example to understand this pattern. So let's say I have a context where I am seeing lemon, a tablespoon of apricot jam, a pinch of whatever salt, and so on. And say apricot is my target word, and everything else is so I have a context window. So tablespoon of jam A is my context. So I create, given the target apricot, I create positive examples using the context tablespoon of jam A, and I do negative sampling by sampling from the unigram probability to the power 3 by 4. Right. So like aardvark and my, where, coaxial, 7, forever, DRF. So some examples, some negative samples that I may get. Right. So these are some positive samples, some negative samples. Now, what exactly happens? So you have probability of a positive sample given WC should be 1, apricot tablespoon should be 1, of apricot off should be 1, jam should be 1, right? And this is modeled using sigmoid function. So this is how sigmoid function looks like. So if you have a high value as the input in G, you get this probability close to 1, right? So I want to model this thing. If embedding similarity is high, then probability is high, right? So G should be, the input should be the embedding similarity of W and C. So I'll use the embedding similarity of W and C as the input to the sigmoid, and I'll say 1 upon 1 plus e to the power minus embedding similarity of the positive samples, right? So the probability that this is a positive sample given W in the context, so it will be nothing but for all context Ci probability plus k1 W Ci, and this I'll model using embedding similarity. So 1 upon 1 plus e to the power minus Ci dot W, right? And I take a log of this, so this becomes this formulation, right? And this we have seen earlier as log of 1 upon 1 plus e to the power minus Ci dot W, another way of writing this, right? So given a target word W and its context window, So, you assign a probability on how similar this context window is to the target word, right. And this probability is obtained simply by applying sigmoid function to the dot product of the embeddings. So, you have these are the parameters you are learning as we saw last time. So, for the same V words in the vocabulary, you are learning W vector and C vector, two different vectors are being learned. So, target word and context word, right. Now, so let us say we take k negative samples. So, we have probability of this positive samples and negative samples, right. And this I am modeling as 1 minus probability of this being positive sample. So, this turns out to be log sigmoid over positive context time W and log sigmoid over minus embedding of negative sample times W, right. So, this is very similar to what we had seen here, right. This is exactly same as what we had seen here for positive sample and negative sample. Okay. So, essentially what I want to do, I want to minimize this loss. So, that means I have to maximize this quantity, and this will happen if, so we saw if the sigmoid, this will be maximum if this embedding similarity is high, right. So, I want to maximize the embedding similarity of the real target context word pairs W in C positive. At the same time, I want to maximize this quantity, means this is a negation, that means I have to minimize this quantity. That means that I have to maximize the distance, embedding distance between the target non-context word pairs. So, W and C negative. So, I have to maximize the distance between them, right. That is essentially what I have to do. You can also see that by applying the gradient descent, you try to compute the derivative of loss with respect to positive and negative samples. So, this is some exercise you can do. So, you will obtain this formulation, and this actually tells you the same thing. So, for a positive sample, you would end up in moving this positive context and the word embedding closer to each other, so that you increase this. On the other hand, for negative sample, you will end up putting them far apart. So, you want to put say apricot and say negative sample like matrix, Tolstoy to be far apart. So, that is what this learning algorithm would aim to achieve, and that is what you want to do. For a target word and context word, they should have high similarity in the embedding, and target word and negative word, they should have low similarity in embedding, they should be far apart. So, this is what we achieve using negative sample formulation, right, much more efficiently, because now what is happening, you are only doing it for one positive sample and k negative sample. So, that's all the similarity that you are computing. But on the other hand, in the original formulation, you were computing similarity for one word, the positive sample divided by all the V tokens in the vocabulary, right. So, you were computing V or V plus 1 similarity, embedding similarities. Now, you will do only k plus 1 embedding similarities, one positive and k negative, and k is much smaller than V, and that is how you gain speed up in your algorithm. So, now there is another alternative formulation for reducing the time taken in this softmax formulation, and this is very popularly known as hierarchical softmax, and this has been used even beyond learning this word vectors. So, what is the idea of hierarchical softmax? So, what you do here, you use the idea of a binary tree to represent all words in the vocabulary. So, the words, all the V words in the vocabulary will be denoted as the leaf nodes. So, they are all in the leaf. So, there are V words in the leaf, right. And to be able to achieve them as leaf, you need some non-leaf nodes. So, you will have each non-leaf node. So, starting from the root node, you have 2 nodes, 4 nodes, and so on at different labels until you achieve the final non-leaf node. Now, interestingly, what happens? You do not have any learnable vectors for these output words. So, there is no learnable vector associated with the output words. Instead, the learnable vectors are associated with all these non-leaf nodes. Yes, each non-leaf node has a learnable vector, right? And that is what is interesting. So, you do not have a specific learnable vector for each of the leaf nodes, but only for the non-leaf nodes. So, how does the learning happens? So, again you will have an output and a context, right. So, you will have a target and a context. So, what you will do, so let us say I want this W2 be target or context, and depending on what kind of formulation you are using. Let us say I want to go to W2. So, I have a word Wi and I want to compute similarity of the embedding. So, embedding of similarity of Wi with W2. That is what you want to find out, the embedding similarity of two words. So, what I do, I traverse this path starting from root node to till I achieve this node W2, right. So, each node will have a unique path. So, let us say LW is the number of non-leaf nodes. In this case, 1 non-leaf node, 2 non-leaf nodes, 3 non-leaf nodes. So, there are 3 non-leaf nodes in the path from the root to W2. And let us say and Wi is the ith node on this path with vector V and Wi, because they are all learnable vectors. Right. Now, how do you model this similarity? Right. So, for each inner node what they do, so there is a nice trick that they do. So, they say okay. So, for let us say I am at this node. Right. So, let us say I am at this node. So, I can either go to here or here. So, one of them they call it the CHN. So, always the left node is called CHN and the right one is not CHN. Right. So, you make use of the fact whether you are going left or right. Right. So, you do something different if you are going left, and you do something different if you are going right. So, you call this CHN. So, left node is called the CHN and right node is not CHN. Now, the probability of a word W, a leaf node given a Wi, some arbitrary word, one of these words only, but this is not in the tree. You have this embedding. So, you have the embedding of this, but you do not have the embedding for any word in the leaves, right. So, you want to compute this probability of W, this is in your tree, given a Wi node, right. How do you do that? So, we say okay, we follow the path from root to W. So, follow the path from root to W. So, while you are following the path, so we say that let us say there are LW nodes, LW non-leaf nodes on that path, 1 to LW nodes. So, for each non-leaf node, what you will do, you will see the next node that you are seeing, is it CH of the previous node, right? Is it to the left of the previous node or not, right? So, it will be either left or right in the binary tree. So, if it is to the left, you have this function. So, this is 1 if it is true. So, if it is to the left, you say it is 1 if left and say minus 1 otherwise. So, that is this function, and then you multiply with the learnable vector at that node. So, Vn transpose Vn Wj times Vwi, the embedding for the ith word. So, that you already have, that is also your learning, but you already have separately, and this you will multiply it every time. So, let us say in this case W2 given Wi, what will be this? So, I am going left, so I will use positive, again left positive, and then right negative. So, and W1 left and W2 left and W3 right. So, whenever I am going left, I will use plus 1. This will be simply Vn transpose W21 times Vwi. Again a left, so Vn transpose W22. So, embedding of this times embedding of Wi plus embedding of this times embedding of Wi, and here I will use a minus. So, minus of embedding of this node times Wi, and they are all sigmoid multiplication, right. And we know the impact of sigmoid over positive and negative things. Now, this is how you model this probability, right. You compute this probability and you update if this probability is if this probability is low or high. So, you compute the minus log probability as your loss and accordingly update all the parameters. You want to achieve high probability if this is the context word, right. We are not doing negative samples here, we are directly computing the probability of a context word given a target word, right, using this formulation, and you will update all these intermediate nodes so that you can achieve whatever you wanted to achieve. I mean, you wanted to achieve a high probability whenever this is an actual target context pair, and low probability otherwise, right. So, you update your intermediate nodes so that this happens. So you are still trying to minimize this, as we mentioned, minus log probability. So instead of updating the output vectors per word, you update only the vectors for the intermediate leaf nodes, right? And of course, there are many nice tricks that can be done to improve this representation, like what if some words are having high frequency versus some words that are having low frequency. So if some words are having high frequencies, you are visiting them again and again. So you may want to reduce the path length to that. Right now, each word has the same path length. So you can use ideas like Hoffman tree to improvise on this and so on. Right. So there is one question that I have so that you get more idea on how this works. So suppose you are using this hierarchical softmax to compute the probability of the context word given the center word. The target word is there, for which you know the embedding, but the context word is in the tree. So you have to traverse the tree to obtain the probability. So at a given time during training, the center word embeddings are these, and the path to the context goes via 3 nodes from root. So you have the root node, then you go left, then you go right, and then you go right. Right, and this is the node that you are interested in. Yeah. And you would have embedding at each of these, and they are learnable vectors. So they are given to you 1, 2, and 3. Question is, what is the probability of the context word given the center word? Okay. So how do you compute it? So you have W as the center word and W is the context word. So probability W given WI is given by. So you go through the entire path. Each path you do sigmoid over. If the next word is the CH, that is the left node. If so, you do +1, otherwise you do -1 times the vector for that node and vector embedding for the center word. So fine. So one is 1 left and 2 right. So we can first compute these vectors for all the 3 pairs. So this embedding 0.3, 0.1, minus 0.1, 0.05 times this embedding, you compute similarity, you get 0.23. Similarly, this with the next node embedding minus 0.29, this with the third node embedding, you get 0.48. And now you go either left or right. So sigmoid, first time I go left, so 1, sigmoid of 0.23. Next time I go right, so minus of this, so sigmoid of 0.29. And then I go right again, so sigmoid of minus 0.48. And you compute the value sigmoid, multiply these, and this is the probability that you get, 0.1218. So you can try and work it out, and you can even change the order and see what happens, right? So this is the probability, and then accordingly you will compute the loss and update all your parameters in the hierarchical softmax. Okay. So this is skip-Graham and negative sampling, and that we have seen, or even the hierarchical softmax version. So we learned 2 different sets of embeddings. One is the target embedding and the context embedding. So we were having multiplying with 2 vectors, one the center word, one for the context word. Now the question is fine. So after you have learned all that, right? So what do we do with this matrix? What is finally usable? So we don't need the network anymore after we have learned. We can throw away the network. But what we need are the embeddings. So the task is not so important after that, but we need the embedding matrix. For each word, ith word, I can take the WI and CI, and I can add that. Although some people have tried taking individually one of the other, but you can simply add these 2 and use that. Okay. So to summarize, how are we learning this word2vec? So we started with V random d-dimensional vectors as the initial embeddings, actually 2 sets of these. Now train a classifier based on embedding similarity, right? So we took a corpus, pair of words that co-occur as positive examples and that do not co-occur as negative examples, and we trained a classifier that distinguishes between the 2, right? So it will try to take the embeddings of positive pairs close by and embeddings for negative pairs far apart. And finally, once we are done with this training, you throw away the classifier code, just keep the embeddings, right? and we can add the embeddings wi plus ci. And in between we learned some nice tricks to optimize the task, like this negative sampling and also a hierarchical softmax, right. So I hope you were also able to see why hierarchical softmax is much more efficient, because you will only compute similarity for LW nodes, right. So number of nodes in the path, that will be the logarithm of the vocabulary size, right. So this will be much more efficient than computing for the entire vocabulary. Okay. Now finally, we will also look at another way of capturing the word vectors, that is, can we not use the co-occurrence directly? So the distributional semantics, we talked about word co-occurrence, right. So window based co-occurrence, for example, we can use window of size 5 and 10, and that's what we were actually doing in word2vec. We were using windows. In the window we were taking one target word and some context words, right. But what if I go through the entire corpus and compute the statistics beforehand, right? So let's say I have like this simple example. I have a simple corpus with 3 sentences, and I take the entire sentence and I will just count that how often I occurs with deep, I occurs with learning, I occurs with NLP, and I occurs with flying, and I compute it for the entire corpus. So can I not use this co-occurrence directly? Now we have already seen this. The problem with this is that for each word you will have v-dimensional vector, right, v-dimensional vector. Now how would you use this v-dimensional vector, and how would it compare to a d-dimensional vector that we are learning, dense vector? This will be much sparse. So how do you use this statistic to obtain a sparse, a dense d-dimension vector, low dimension dense vector, right? So simple count co-occurrence vectors. The problem is the vector size increases with vocabulary. They become very high dimension, a lot of sparseness, but they require a lot of storage, and this sparsity issue will always come. Right? Models become less robust. So instead we want to still go with low dimensional vectors like we had achieved in word2vec, and you want to obtain most of the information in a fixed small number of dimensions like 100 to 300, right. Now question is, how do we do the best of both worlds, that we still use the co-occurrence statistics from the entire data at once, but use some low dimension vectors to denote these. And that's where the idea came in GloVe vector formulation, right. So this is a nice example that shows how this actually works. So you are seeing two words, ice and steam, right, and what you are doing, you are writing the probability of any context word coming, the probability of any word k given ice, right. So what is the probability of a word k coming with ice, and similarly with steam? And example is being shown with solid, gas, water, and fashion, right. So you get a lot of different type of probabilities, right, and there is a lot of noise that comes in. So what the authors of GloVe paper found, if you take the ratio of these probability k given ice given probability k given steam, then you start seeing the pattern. So you see, okay, so solid is something that distinguishes the two, right. Solid has much more occurrence with ice than steam. Similarly, gas distinguishes the two because gas co-occurs with steam and not with ice, while water does not distinguish. Water occurs with both, and fashion does not occur with any of this. So fashion also does not distinguish between them. So that means if I take this ratio of the probabilities, this can be a good metric. So how do we capture this ratio of co-occurrence probabilities? Like, this is not very straightforward to what we were seeing in co-occurrence. We are computing ratio of co-occurrence probabilities, and can I connect it with some sort of linear meaning component in a word vector space? And that's where they came up with this idea of log bilinear model. So let's say, okay, let's say I say for word I and word j, the dot product of their embedding vectors, I am modeling it as log probability I given j individual. Then I can use the vector difference wx wa minus wb to denote this ratio, right. So because if I subtract minus log probability, so think about x given a probability x given b. So log x given a, log probability x given a minus log probability x given b will be simply log probability x given a divided by log probability x given b, and our job is done. So we have got a co-occurrence ratios, right, and this can be captured as the vector difference, right. So that means if I model using a log bilinear model, the wi dot wj should denote log probability ij, then the vector difference will denote this co-occurrence probability. So they went ahead with this formulation that okay, I want to ensure that the dot product of two vectors that I would achieve, I don't know what are the best vectors, but this is my formulation that this should be close to the co-occurrence probability I given j. Okay. So wi transpose and wk hat, again I will have to kind of word vectors, will be log of pik, right. So what is pik? The co-occurrence probability that ik occur together minus probability of I, right, minus log xi. So pik is xik divided by xi. Now this does not look very symmetric. So what they did, they said okay, I can include some bias terms. So wi transpose wk hat plus bi, so log xi is absorbed there, but I also introduce a bias term for the other k. So bk tilde is log of xik. So xij, okay. And then so xij is simply co-occurrence frequency of I and k, and then I say okay, this should happen. So I have a function that says I want to optimize this, so minimize this loss, wi transpose wj hat plus bi plus bj hat minus log xij square. I have a least square formulation. Now again there is some trick because you can simply use this, but what will happen, some pairs would co-occur a lot and some pairs will co-occur less. So you don't want to give some pairs a lot of advantage, I mean lot of say in this formulation if they are co-occurring a lot. So this function, they use a function of xij to multiply with this. So if this function, so you just clip it, if it goes beyond certain value, you just clip it, you don't take more value than this, right. And yeah, you do some trick for the lower co-occurrence thing, so you try to increase their count a bit, increase their say a bit more, right. So you don't overweight with the frequent co-occurrences, and the low co-occurrences you give them a little more weightage. So this is their objective function, and that's all. I mean, the good thing here is you compute xij only once through the entire corpus, and then you are saying my embedding should be such that it should match my co-occurrence count, right, and you have some function to multiply with that. And the authors also try to make a connection between the word2vec and the glove model, right. So let's say, so this is our word2vec formulation. So let's say qij is the probability that word j appears in the context of word I, and we modeled using exponent wi transpose wj hat divided by, for all vocabulary, exponent wi transpose wk hat, right. This was the formulation. So what would be the global objective function that you can write from here? So you have for all words in the corpus, I mean all words in the corpus and all words that occur in its context, right. You want to minimize this log qij, right. This is the objective function, the loss function, that minus log of this probability, right. And this you can write it as, so the actual count, so how many times in the corpus the word I will come with the word j will be just the frequent, the co-occurrence count xij. So you say okay, for all ij, xij times log qij, right. So this is interesting way of connecting with the entire global thing, that you have log qij for one particular co-occurrence but they will co-occur xij times. That is their global frequency. So this is one way of connecting. Now you want to further make a connection between the actual formula of glove. So what they did, they said, okay, so you further take this term and say, okay, I can count the frequency of xi simply summation k xik, and pij will be xij by xi, right. So I can write this xij as summation over I xi, and then I do xij by xi, right. So this will become pij. So xi times xij by xi, and this becomes pij and log qij. And this pij log qij has a notion of cross entropy. So this is like you are doing cross entropy between these two terms, pij and qij. Pi is the conditional probability and qij is what you are getting through here, right. Their embedding similarity. So their actual, so this is their actual probability of co-occurrence, and this is their embedding similarity based probability. So you are doing a cross entropy over there and weighting it by the individual frequency. Right? So it's a weighted cross entropy loss that you get. And this in some way resembles the least square formulation that glove vector proposed. Right? So here also you were seeing the word embedding similarity and what you get from this co-occurrence. Right? So you are trying to compare that. So this is some way connection that they brought between the Stim-Cram and glove vector. So yeah, this completes our discussion on learning the word vectors both through word2vec and glove, and we also try to make a connection. So you can go through our SLP3 book, chapter 6, to get more idea about this. So thank you. We will talk about some more miscellaneous things in the word vectors for the next 2 lectures. Thanks.